Okay, so on Friday, we'll have an Leonard Euler presentation on the formula for the sum of the reciprocals of the squares. Okay, so like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus etc. Like you just go on forever. Question is, does that sum approach some kind of number the more terms I add on? And surprisingly, the answer is yes. And even more surprisingly, the answer is pi squared over 6. What? Right? And it turns out that Leonard Euler was the first person to kind of sort that out. And he basically does it just using algebra, essentially. It's kind of a sophisticated form of algebra that no one had thought to do before. But it's exciting. It's, I think, one of the most clever proofs in the whole book. I think it's just beautiful. So hopefully you will too. And then there's another chapter on Euler. And by the way, here's a hint. If this book spends like 2 chapters on one individual, that usually means that they were kind of a big deal on the mathematical timeline. Euler gets 2 chapters. Cantor got 2 chapters. Archimedes probably should have got 7 chapters. But they only gave him 1, okay? Euclid got 2 chapters, right? Basically, Pythagorean theorem and infinitude of the primes. He was a big deal too. Okay, let's finish cryptography, shall we? So I just wanted to remind you of what we were doing last time. And I'm not going to actually put this in slideshow mode yet because I want to flip over to what we were working on at the end of last time. So first of all, remember the possibility of public key cryptography was proposed before this came about. So there was kind of a philosophical argument that came from some theoretical computer scientists in terms of the possibility that everybody could kind of have their own public key that they would publish. And then like if Monique wanted to send me a message, she would like find my public key and encrypt her message with my public key and send it to me. And Monique wouldn't even have the ability to decrypt that message. I mean, in her mind, she might remember what she wrote, correct? Yeah. But nobody else, including her own self, in theory, would be able to actually decrypt that message once it's encrypted with my public key. So it's kind of like a one-way trapdoor function. And then it comes to me, and I have the critical piece of information that actually allows me to decrypt that message. And it turns out the critical piece of information is how to factor the modulus. Yeah? Factorization of the modulus is the key. Once you can do that, you have in effect cracked the system. And the setup was you had n, remember, so what's this little n? What role was that playing? I don't know if you remember or not, but do you remember what role little n was playing? Yeah, that was the modulus. And E, this is oftentimes referred to as the encryption key or power, okay? Because in essence, you kind of use this thing in raising your message once it's been converted to a number, raising your message to a power and taking it modulo n. And that's what you send across the channel. And no one should be able to crack that thing unless they're superhuman, okay? So to hack the system, you would need to be able to factor this thing, which is hard. Now, what property does E have? Well, it has to be relatively prime to P minus 1 times Q minus 1. It might not be clear why that happens to be the case yet, but in essence, it being relatively prime to that product means that we can find an inverse for it. Yes, that was key. You know you can find an inverse for E modulo P minus 1 times Q minus 1. And by the way, if I know P and Q, I will also know P minus 1 and Q minus 1, right? And so as a hacker, If I figure out what P and Q is, because you've published your modulus, yes? If I figure out what P and Q is, then I would know what P minus 1 times Q minus 1 is. I would take your encryption key, E, and I would just find an inverse, and I would be able to sit there and just listen to any messages that you send across the channel, yeah? That's how this would work. So the minute you know P and Q, you've hacked the system, okay? So why on earth do we want this thing to be relatively prime? Well, first of all, so we can find an inverse, and that will be our private key, but we'll see more clearly later on why that's important. Oops, what is happening here? Okay, here we go. Okay, so we talked about that you have to kind of figure out how to break your message up into blocks, remember? So what you did is every letter in your message, you converted to a 2-digit number. So like A was 00, B was 01, all the way to Z, which is 25, yeah? And so every group of 2 digits represents 1 letter, which is why there's all this stuff about N and 2N, right? N is number of letters, 2N is the number of digits that would translate into, yeah? And how many letters can I take at a time? Well, it's basically the number of 25s I can string together and still stay below the modulus, yes? Right, so if the modulus is 38,021, I can string together not just 1, but 2 25s together and still stay smaller. But if I try 3, that's too big, correct? And so that means if I can do 2 25s and still stay below the modulus, that means I can send 2 letters at a time across the channel. Once I do that and kind of break the thing up into the appropriate size chunks, I simply take the message I want to send, raise it to the E power, and take that modulo N, and that's my ciphertext, or my crypto text, or my my encoded text, or whatever. And that's what I send across the channel, and no one should be able to break that thing. So I get a bunch of ciphertext blocks that I send across once I encrypt them. Okay. So Monique has published N and E, and I say, here's my message. I break it up appropriately because I can see the modulus. It's right there, right? I raise everything to the E and take it mod in, and I send it across to Monique. Yeah, send it across to her, and she's able to decode those things. But not me, or any of you for that matter. Okay. Last time we kind of worked on this one, didn't we? We sort of tried to encrypt the message 4, right? And there, right, we noticed that, look, 38,021, first of all, that's 193 times 197. So my 2 primes are 193 and 197. By the way, any hacker worth their weight in gold would crack this system in 8 seconds, okay? Maybe less, okay? This is way too easy. You would need to use massive primes. It's just for illustrative purposes, okay? How many 25s can I string together to still stay below this? 2, right? So how many blocks does that translate, or how many letters does that translate into? 2 letters. So I can send 2 letter blocks, right? So the blocks are going to be 2 letters. So that means I would kind of break this thing up into FO and UR, and I would send that across once I encrypt those things. And we were kind of doing that last time, if you will recall. What was that? Can you guys help me out here? What was FO? What was FO equal to? 0514, yeah. Which by the way is really just the number 514. And what was UR? 2017, right? 2017. Yes. Okay, so in the notation on the previous slide, this would be my M1, and this would be my M2. Okay. And then we encrypted these things. Okay. We encrypted these things. We said, all right, 514. What am I going to raise it to? I would raise it to the 25. Okay, let me see here. I think I think I still might have this up over here. Maybe not. I'll open up another thing here. So here's Wolfram alpha. So we would go 514 to the what? What do I raise it to? To the 25th, right? Because E was 25 for us. Right, so E was 25. That was the encryption power. Okay, raised to the 25 mod 38021. And we got this. Okay, 13,070, right? The 13070. So that's the thing we would send across. That would be like C1. Okay, C1 is equal to M1 to the E mod N. And in this case, that ends up being 13070. But you'll also recall, maybe, that we went over here and like, because I knew what the primes were, I put them in here, I set P and Q, here's what N is. Unfortunately, they use capital N, right? We use little n, whatever. We look at P minus 1 times Q minus 1, and that's this number right here, 37,632. I look for things that are 1 upon division by that, yes? So clearly, I mean, you guys understand 37,633 is clearly 1 modulo 37,632, yes? As a remainder of 1 upon division by that. But all of these guys do as well. And what we did is we hunted around for something that was divisible by 25. Because Monique, if this was Monique's public key, 25 is the thing I want to check for divisibility into one of these things, yes? So like this guy right here is clearly divisible by 25. We use that one down here. We factored it, okay? And we said, hey, that's just 25 times this disaster right here, yeah? And we said, well, I'm going to set that equal to D. So 25 times 10537 equals 263,425, which is really 1 modulo P minus 1 times Q minus 1, yes? So this E and D, when I multiply them together and take it mod, in this case, right, it's P minus 1, Q minus 1. We have a specific number here, but that is 1. Okay, where E and D are these two numbers, right? And it turns out so long as E and D are inverses of each other, modulo P minus 1 times Q minus 1, we will be able to decrypt things. Okay, so let's go back over here. So what did we say D, what was D again? We found out that D was, yeah, 10,537, exactly right. So if I go back over here into Wolfram alpha, I take this number 13070, for instance, and I raise it to the inverse of E modulo P minus 1, Q minus 1, not N. Don't mix N and the other thing together, right? It's important to not mix those up. So it was 10,537. I hit enter. And what do I get? I get 514 right back. Yes? So again, I use Monique's public key to encrypt my message, send it across 13070. She would use an inverse of that thing. She could have used 10,537, but there are other choices as well that would also work. And she basically raises it to that power, takes it mod 38021, and is able to decrypt the thing. Yeah? So does the process at least make sense? You have the public key. There's a private key that you keep private. You kind of use that in decoding the thing. Just want to make sure we're kind of clear on that. We'll see why all of this stuff is actually working here pretty soon. Okay? Any questions on that before we move on? Any questions? I don't know. I think that's pretty cool that it even works. Yeah, I mean, why it works is another question, but we just saw that it worked, correct? Right? We kind of decrypted FO into this crazy number 13070, and then we were able to take the private key and decrypt that thing and get 514 back. It's amazing. Okay? So once again, starting from sort of the ciphertext blocks, you decrypt each block by taking C to the D mod n, yeah, each of the ciphertext to the D mod n, and that will give you the message right back. The only stipulation is that D has to be an inverse. D is the so-called private key, okay? D has to be an inverse of E modulo P minus 1, Q minus 1. Okay? Again, the whole reason that this system doesn't, isn't vulnerable on its head is because it's hard to factor numbers. That's it, okay? And maybe someone went and solved factorization of numbers and chucks after last lecture, but hopefully you kept that to yourself, okay? If you didn't, then you probably wouldn't be here right now. Yes, Joseph. Yes, I would give you an automatic A in the class. But I mean, you might not live to get that A in the class. Yeah. Yeah, you get an A in the, yeah, right, you get an A on the final, therefore you get an A in the class, yes. You would also be very rich or very dead or both, yeah. So both of those things would probably be true, okay? So why does this work? Let's talk about that, okay? Let's talk about why this works. Okay, and here's the explanation. We're going to talk through this carefully together. Okay, so here's kind of the verification. Okay, so man, what is going on with this? That's annoying. Why is this C kind of doing that? Oh well. Suppose someone intends to send us the message M, which is encrypted by doing C equal to M to the E mod n. Yes. Okay. So C is our ciphertext. And they've used our public key, and N happens to be PQ. D is private, right? Even the sender can't decrypt this ciphertext, right? So they wouldn't be able to decrypt. They take the ciphertext to the D mod N because they don't have D, unless they can factorize N. And then they would be able to find their own private key and cheat the system, okay? Of course, seriously, if I'm sending a message to Monique and I decrypt using her, or I encrypt using her public key, I know the message in my mind, correct? But I still wouldn't be able to decrypt the message physically once I've encrypted it, okay? So to decrypt the ciphertext, you compute C to the D mod n, which really, think about it, remember C was M to the E, yes? Mod n, correct? So this is kind of the first step in the verification process. You know that C, this is annoying, C is equal to M to the E mod n, correct? So when I go C to the D, it's really like doing M to the E raised to the D, yes? Because C is M to the E mod n, yeah? So it's really like M to the ED mod n. That's what's really going on when we try to decrypt this message. Does that make sense? C is like M to the E. So when I raise C to the D, it's like raising M to the E times D, yeah? So that's kind of the first thing you have to realize. Okay, you guys realize that E times D is basically 1, modulo P minus 1 times Q minus 1, correct? Well, what does that mean? That means that ED is equal to 1 plus some multiple of P minus 1 times Q minus 1, correct? E times D is equal to 1 more than a multiple of this stuff, right? That's what it means to have a remainder of 1 upon division by this, yes? It's this number, P minus 1, Q minus 1, times an integer plus 1, yeah? Okay, so that's what it means for E and D to be inverses of each other modulo this thing. Okay, so let's see if we can follow the trail here. M to the ED, just replace ED by by what it equals. It's 1 plus P minus 1 times Q minus 1 times K. right? No qualm there. We've just replaced ED by what it's equal to. Do you know what I'm saying? Okay. And check this out. Like this is kind of silly, but like P minus 1 times Q minus 1 times K, that just means that's the same thing as P minus 1 added to itself a bunch of times. Right? That's what I'm writing right here. You have P minus 1 added to itself how many times? Q minus 1 times K times. Yeah? I mean, seriously, if I have A, B, and A and B are positive integers, then this is like A plus dot, dot, dot plus A. How many times? How many times do I add A together? B times, yes? And that's exactly the same thing that I'm doing here. I say I have P minus 1 times Q minus 1 times K. That's the same thing as P minus 1 plus P minus 1 plus P minus 1, a total of Q minus 1 times K times. Yeah? Now, you might say to yourself, why does that matter? Well, what I'm going to do is put one of the, okay, this is important. I'm going to put the 1 with P minus 1. What's 1 plus P minus 1? Hello, yeah, it's P. Excuse me, right? So I take one of the P minus 1s and I put it with 1 to give me P. So now how many P minus 1s do I have? Before I had this many P minus 1s. Now how many P minus 1s do I have? Well, I have one less than that. Yeah? That's why I take that same number minus one of those, because I peeled off one of the P minus 1s. Yes? Okay? Now that's important. So just make sure that we understand that. I basically, instead of having P minus 1, Q minus 1K, I wrote it as a sum of a bunch of P minus 1s. I combine a P minus 1 and a 1 to give me P. And that means I have one less P minus 1 in that sum. Yes? I have one less. Yeah? Okay. Well, excuse me, what is M to the P if I take that? Okay, look, I'm actually going to work mod P. Why? Because I know Fermat's theorem, don't I? Yes? Fermat's theorem says M to the P is the same as M modulo P. Does that make sense? Yeah? M to the P is the same as M mod P. Remember, because Fermat's theorem said P divides M to the P minus M. Yes? Okay. So what I can do is instead of having M to the P, I can apply Fermat's little theorem and replace that by just M to the 1. You see what I'm saying here? Yeah? Okay. And again, I'm working modulo P, and you might be saying, wait a minute, we're supposed to be working modulo N, not P. But just hang on, okay? I'm working modulo P here for a minute. But then what can I do? Look, well, now I'm back to where I was up here, basically. Okay? I have 1 plus a bunch of P minus 1s, yes? And I just keep peeling off those P minus 1s and combining them with the 1, and I repeatedly apply Fermat's little theorem over and over and over again. Yeah? I just keep saying 1, peel off a P minus 1, 1, peel off a P minus 1, 1, peel off a P minus 1. Give me P. M to the P is just M by Fermat's little theorem. Yes, modulo P. And eventually, what am I going to do? I'm going to run out of P minus 1s. Yes, aren't I just going to eventually run out of them? And what will I end up with? I'll end up getting M modulo P eventually. All of this computation is being done modulo P. And you invoke Fermat's little theorem many times if necessary, yes? You just keep kind of combining the 1 with the P minus 1 for as many times as you need to until you get down to just M itself. But again, one thing I want to point out and continue to point out is that all of this computation is being done modulo P. Note well the importance of P minus 1 in this scheme. Okay? The P minus 1 is combined with the 1 to give me P. Yes? You remember we were like P minus 1, Q minus 1. What in the world is going on here? Yeah? Well, it turns out we've seen why P minus 1 was important right now. Basically, it's important because P minus 1 plus 1 is what? P, and Fermat's little theorem tells us something about m to the p. It's m modulo p, okay? All right, so basically m to the ed, look at all this right here. All of it says that if I work modulo p, m to the ed is just m modulo p. Okay, so if I was working modulo p, I would get my message back. That's what this says, yeah? This is saying if I was working just modulo p, I would get my message back. That's good. That's at least part of the way there, but I don't want to work mod p. What do we really want to be working? Mod n, okay? Well, just chill out for a second, okay? We'll see how we can kind of get there here, okay? So watch this. M to the ed mod p is just m mod p. That's what we basically just showed, yes? M to the ed, remember m to the e was when we encrypted the message. Then we raised that to the d to give us m to the ed. If I work mod p, I get m right back, the original message. But also, couldn't I work mod q? We can make the exact same argument mod q, the other prime. And you'll get m to the ed mod q is just m mod q. Okay? So what does that mean? That means that p divides, and this is really the whole game. P divides that difference. If m to the ed is the same as m mod p, and m to the ed is the same as m mod q, okay? Then that means p divides that difference between m to the ed and m, and also that q divides it. P divides it and q divides it. So that'd be like 5 divides this number and 7 divides that number. 7 divides, right? 5 divides that difference and 7 divides that difference. These are two different primes. But if 5 divides a number and 7 divides a number, then what will also divide it? 5 times 7, right? If 5 divides it and 7 divides it, then 5 times 7 will divide it because those two things are relatively prime, yeah? If 7 divides a number and 13 divides a number, then what else will divide it? 7 times, I forgot what did I say, 13? 7 times 13 will divide it also, okay? Since P and Q are two different primes, you know that N, which is equal to PQ, will divide that difference. And now, my friends, you are done. Because you've just shown that the product of P and Q, which is N, divides that thing, which means that M to the ED mod N is really just M mod N, which, by the way, is just M. Because M, after all, was a message like built. It's actually a block. And that thing was smaller than the modulus in the first place. So we get the message right back. Yeah? That's sort of, I think that's amazing. Okay? So let me just say, in understanding this scheme, it's easy to see how you might adjust it to accommodate a modulus that is the product of any number of distinct primes. Remember, somebody asked, what if you accidentally have a number that's the product of a bunch of primes? Yes? And it turns out you could do the same sort of thing that we just went through, and you could show that the scheme still works. Yeah? It was, you would have, instead of P minus 1, Q minus 1, you would have P minus 1, Q minus 1, like R minus 1 or something, where R was a third prime, for instance. Yes? And you would go through the same thing and show that it works. But it's not as secure if you have a number that's a product of a whole bunch of different primes, because people could stumble upon one of them more easily. Okay? Look, this is sort of stupid. I don't even know why I have this in here, to be honest with you. So like, suppose N was just the number 30, or was just 1 prime, okay? Okay? Suppose N was just 1 prime, like 37. Suppose E was 5 and D was 29. You could check it out, but if you take 5 times 29, that's congruent to 1 mod 36. So this single prime scheme will actually work, but it would be pretty stupid scheme. I'll let you think about why that happens to be the case. You can go, like, if you just use a single prime, it's very, very insecure because, hello, your public key would be the prime. And therefore, you could just you would be able to immediately come up with the private key on your own, or one that would work. Yeah. Okay, so that's not very secure because you're literally broadcasting the prime that you're working with. But when you have a product of two, it sort of keeps that information hidden from sight. Okay. All right. So what about this? Here's an example. Okay. So suppose you receive this message. Okay. Suppose you receive this message. So this is a couple of blocks like this. We just received this. What is the decrypted message if it was encrypted using the RSA scheme with this public key? So first of all, I'm telling you, and by the way, any hacker would be able to figure this out immediately. That number 2537 is just 43 times 59. Okay, and by the way, if we've really encrypted or if we've really implemented the RSA scheme, this is my N, this is my E. Okay, so the public key is that modulus and that encryption power. How many letters would we be sending across the channel at a time? How many letters would we be sending across the channel at a time? 2, because 25, 25, that's the number of 25s I can string together and still be smaller than 2537. If I try to tack on another 25, it's no good, right? So we... How many? Okay, we encrypt the letter A with 00. We encrypt the letter B with 01. So in order to accommodate any one of our letters in our alphabet, there are 26. Therefore, what's the largest 2-digit number I would need? 25. Make sense? And incidentally, you could do more than that if you wanted to. You could say 26 is exclamation point, 27 is asterisk, or something like that. You could accommodate other things if you want to, but you would just have to change the scheme slightly. Okay? Make sense so far? So this is what we got. We received this message. We received 981. Okay, basically. And we received 461. Okay? And this was with N equal to 2537. Which is 43 times 59, and with E equal to 13. Notice, what have I not told you here? What have I not told you? The decryption key, the private key, has not been told to you. Yeah? But since I know the primes, guess what I can concoct on my own? A private key. Okay, so let's go do that. So, let's go in here. Okay, so what were my numbers again? 43 and what? 59. So I set P and Q. All right. Okay, so P minus 1 times Q minus 1, which by the way, in our case, P minus 1 is 42. And Q minus 1 is 58. Okay, so if I multiply those together, apparently I get 2436. And this right here is everything that is 1 modulo 2436. And I need something that is divisible by 13, correct? I mean, I want something that's actually divisible by 13. Okay, now let me... help me out here. See this list of numbers that's right here? So take a few minutes on your calculator and find one of these that is actually divisible by 13. Okay? We're hackers right now. That's what we are. We're like, okay, we need to find a private key. That's going to amount to figuring out which of these numbers, if any, is divisible by 13. Okay, so do that here for a minute. See. So the claim is 12,181 works. Okay, so that means let's choose K to be 12181. which apparently is divisible by 13. Okay, so let's make sure that that's true here. Erase this. Okay, so let's see, factor K. 13 times 937. Aha. Okay, so that means what should we take D equal to? Yeah, D should be 937. D should be 937. Okay. And down here, they do various checking things. So RE is 13 and 937. And let's check E and D just to make sure that things are going to work. Okay, so 2537 is N, R is that, E times D is that, which is congruent to 1. E and R are relatively prime, D and R are relatively prime, and they are inverses of each other. This will work. Yeah? So it just kind of checks everything for us. So back to, let's go to Wolfram alpha. Okay, and let's decode these things. So 981 raised to the, okay, what am I going to raise this to? That was the encrypted message that was sent across the channel that I have intercepted as a hacker. Yeah? What am I going to raise this to? 937 modulo, and I'm going to, what's our modulus? 2537. Okay, that's funny. Some people must have already plugged this in, okay? Because Wolfram alpha knows. Okay, so I get 704. So let's see, I go 981. I'm just going to write this down. 981 to the 937 mod 25 mod n, I'll just write n for short, equals 704. So I'll write that as 0704. Okay. And what was our other one? 461 to the 937 mod n. And again, we're decrypting here. Decrypting. Okay, so let's see. 461. Okay. Raise to that thing, and I get 1115. Okay, so what letters do I have here? So what's the, remember 7 is really the 8th letter in the alphabet. A, B, C, D, E, F, G, H. Yeah? Okay, so this guy right here is H. Huh, okay. 4 is really the 5th letter in the alphabet. A, B, C, D, E. 11, okay, well, let's see here. H is the 7th, okay. 4 more, H, I, J, K, L. Okay. Okay, and then 4 more beyond that. M, N, O, P. Okay. Now, sometimes you have to sort out which order to put these things, but it's fairly obvious in this case that we should do H, E, L, P. Does that make sense? Okay, so there it is. Yeah, we were able to sort of decrypt this thing, which is pretty neat. Any questions on that? Let's go back over here real quick. Oops, what is happening here? This right here, okay? So we decrypted that, we found out it was help, okay? I do wanna this is the last slide that I have, okay? I do just wanna talk about how can I tell that someone isn't pretending to be someone? You know what I'm saying? Like, what if Monique is like pretending to be me? And she sort of says, hey, I'm Hammett, and I'm going to publish this public key. So if you ever want to send a message to me, Monique pretending to be me, yes, please encrypt the message and send it to me, yeah? So what if there's like some German espionage center of some kind that's pretending to be American, yes? They say you want to send a message to the Pentagon, then you should use this public key. So how can we be sure that a message is being sent to the entity we want it to go to. Yeah? Well, it turns out there's a cryptographic protocol called a digital signature. And I'll just briefly describe what happens here. So it's, again, this is a way of ensuring that the recipient, that the message came from the claimed sender. Yeah? What you do is you append your name. You append your name to the message by encrypting the name with my own private key. So what I do is like, I use your public key, but I use my private key to encrypt my name, right? I use you know, like what's going to be my public modulus, but I encrypt with my private keys. Does that make sense? So like, I actually use the public modulus that I've published for everybody to see, but I encrypt with my private key. So I put Hammett and I encrypt that. Now everybody will be able to decrypt that, yes? With what? The public key, yes? Everybody will be able to decrypt that. But the only person that could possibly have done what just happened is me, the one who has the private key, yes? So once again, I kind of append a signature, namely my name, using my private key that no one else has, and my published modulus, and everybody on Earth could decrypt that with the public encryption key. You kind of use things backwards. And that guarantees it came from me. And I kind of append that to the message that I send with like Monique's public key. Does that make sense? So like I use her public key and encrypt the message and send it across. But I append that digital signature that everybody on Earth will know, oh, Hammett is sending a message. The Germans will know, the Chinese, the, you know, Iran will know, North Korea will know, but who cares? They just know I'm sending a message. They're not going to be able to read the actual message itself, yes? So that's the way that you can kind of make sure that everybody knows that this is really coming from Trump or something, right? Yeah, okay. All right, any questions on that? All right, well, that's the end of our number theory explorations. That's it. Okay, so now you know the RSA scheme, you know the number theoretic underpinnings, and you can wow your friends. Okay.